Method of integration by partial fractions. In this video, we will see a procedure for decomposing a rational function into simpler rational functions, to which you can apply basic integration formulas. To decompose a rational function into simpler rational functions, we sometimes use long division as a preliminary step. If you don't remember how to do polynomial division, watch the video shown in the upper right corner of the screen, where I describe how to do polynomial division using long division as well as the synthetic method. Thanks in advance for watching this video. If you like this video, don't forget to like and subscribe to the channel and activate the bell. It's very important for the continuity of this channel. A rational function is a quotient of two polynomials. The method for rewriting rational functions as a sum of simple fractions is called the method of partial fractions. Method of integration by partial fractions is the name given to a technique of integration that expresses a rational function as a sum of simple fractions, called partial fractions, which are easily integrated. We have seen some techniques that allow us to integrate specific rational functions. For example, we know that in some special cases, integrals of rational functions can be found by simple substitutions. Look at these two examples. In the first integral, we use the substitution t equals x minus 3, then dt equals dx. Making this substitution then gives the answer. In the second integral, we use the substitution t equals x minus 3, then dt equals dx. Since we must convert everything to the new variable, including the numerator, we solve for x to obtain x equals t plus 3. Making these substitutions gives the answer. However, we do not yet have a technique that allows us to tackle arbitrary quotients like these ones. So let us see how the method of integration by partial fractions works. Case 1. If the denominator has the form ax plus b to the power of n, the substitution t equals ax plus b will always work. Let's solve item A. We make the substitution t equals x plus 2, so dt equals dx, and each x in the numerator is replaced by t minus 2. While it may be tedious to complete the integration if the numerator has a high degree, it is merely a matter of algebra. Case 2. If degree of p of x is less than the degree of g of x, we rewrite f of x as a sum of rational functions with distinct linear denominators, and then we integrate term by term as follows. Let's solve item B. The first step is to factor the denominator. In this example, it's quite easy since the denominator is a difference of perfect squares. The second step is to write the rational function as a sum of rational functions with linear denominators, where each factor of the denominator becomes the denominator of a separate fraction. Then, put unknowns in the numerator of each fraction. Since the denominator has two distinct linear factors, the partial fraction decomposition takes the form. The third step is to multiply both sides of this equation by the denominator of the left side. The fourth step is to take the roots of the linear factors and plug them one at a time into x in the linear factors to find the unknowns a and b. The fifth step is to put these results into the a and b in the equation above, and we can split the original integral into two simpler fractions that can be easily integrated. Pay attention. Let's see another example. The first step is to factor the denominator. In this example, the denominator is factored. The second step is to write the rational function as a sum of rational functions, where each factor of the denominator becomes the denominator of a separate fraction. A common mistake is writing the partial fractions as follows. Since the denominator has three distinct linear factors, the partial fraction decomposition could be written this way. But it's wrong, since the least common multiple of the partial fractions on the right-hand side is not the same as the original rational fraction. You should recall that we form the least common multiple by writing each factor to the highest power it occurs in either polynomial. So the x minus 1 in the denominator has a power of 2. So we get two partial fractions for the x minus 1, for the powers of 1 and 2. The x plus 2 has a power of 1. So we get one partial fraction for that factor. We now multiply both sides of this equation by the denominator of the left side. We need the roots of the factors and plug them one at a time into x in the factors to find the unknowns a, b, and c. As we can see, we can solve for all the unknowns by plugging in the roots of the factors. So you have more work to do. We cannot determine a in the same way as b and c. We plug into the last equation the known values of b and c, and we are free to plug in any other value of x. Let's try x equals 0 and solve for the unknown a. We put these results into the a, b, and c in the equation above, and we can split the original integral into three simpler fractions that can be easily integrated. The first and the third integrals are easy. For the second, we use substitution with t equals x minus 1 and the t equals dx. Pay attention. Case 3. If the degree of p of x is greater than or equal to the degree of g of x, then we must take the preliminary step of dividing g of x into p of x to reduce the problem to the case where the numerator has a lower degree than the denominator. After that, we write the integrand in the form. Let's solve item D. Since the degree of the numerator is greater than the degree of the denominator, we first perform the long division. the quotient is 2 times x, with the remainder being 2 times x plus 1. Then we write the original rational fraction as a polynomial plus a rational fraction, where the degree of the numerator is less than the degree of the denominator. The next step is to write the fraction on the right as a sum of partial fractions, as follows. The final step is to integrate. We can see that the integration step is quite quick. Almost all the work is in preparing the integrand. Case 4. If the quadratic denominator can be factored in, so we don't need to use the partial fraction technique. We complete the square and solve the integration by using the substitution method. Let's solve item E. The quadratic denominator does not factor. So we complete the square in the denominator by adding and subtracting the number 4. The denominator in integrand suggests we make the substitution t equals x plus 2. Then dx equals dt and x equals t minus 2. We split the integral and then we evaluate each integral. The first integral is a logarithm, and the second is done with the arctangent rule as follows. Case 5. If integrand has an irreducible quadratic factor in the denominator, so the numerator of the partial fraction that contains the irreducible quadratic factor is written as a linear factor ax plus b. You should remember that the partial fractions must have the degree of the numerator less than the degree of the denominator. So when the denominator contains a quadratic factor, we have to consider the possibility that the numerator can contain a term in x. This is because the numerator would still be of lower degree than the denominator. Let's solve item F. We start breaking up the original rational fraction into a sum of partial fractions. The numerator of the partial fraction that contains the quadratic factor is written as a linear factor ax plus b. This equation has no linear factors, so you can't plug in the roots to get the unknowns a, b, and c. To find the unknowns a, b, and c here, we shall demonstrate a different technique, one called equating coefficients. We take the equation above and multiply both sides by the denominator of the original rational function. We expand the right side of the equation and then collect up like terms. Since on the right-hand side there is one term involving x squared, we rewrite the equation as follows. This is an identity which is true for all values of x. Then the coefficients of like terms from the left and right sides of the equation must be the same. In other words, the coefficients must match. This gives us a system of three equations. Solving this system gives a equals minus 1, b equals 1, and c equals minus 1. So we obtain the partial fractions. We now split up the original integral and integrate term by term. The first integral is solved by substitution, t equals x squared plus 1. The second is done with the arctangent rule. And the third integral is a logarithm. Pay attention. Let's solve item G. We start breaking up the original rational fraction into a sum of partial fractions. In this integral, the denominator contains a repeated irreducible quadratic factor. The form of the partial fraction decomposition is similar to what we made in item C. The x in the denominator has a power of 1. So we get a partial fraction for the x. The irreducible quadratic factor has a power of 2. So we get two partial fractions for it, for the powers of 1 and 2. The partial fractions that contain the quadratic factor are written as a linear factor as follows. We now multiply both sides of this equation by the denominator of the left side. We expand the right side of the equation and then collect up like terms. If we equate coefficients, we get the system. Solving this system gives. We now integrate term by term. The correct form we should take for the partial fractions expansion depends on the factors of the denominator. To make it clearer, below I leave some examples of the correct forms of expansion. Let's solve item H. We break up the original rational fraction into a sum of partial fractions. In this integral, the denominator contains a quadratic term which cannot be factorized. The form of the partial fraction decomposition is similar to what we made in item 8. We now multiply both sides of this equation by the denominator of the left side. We take the root x equals 2 and plug it into x in the factors to find the unknowns a, b, and c. The first term on the right-hand side will be 0, and so a and b will disappear, but we can find the value of coefficient c. Unfortunately, there are no values we can substitute which will enable us to find the values of a and b. So we use the technique of equating coefficients. We expand the right side of the equation and then collect up like terms. If we equate coefficients, we get the system. Solving this system gives. We now integrate term by term, and the hard work begins. Pay attention.